United States, there's many different ways of designing bridges in the past. And so they started with allowable stress design, and later there's a load factor design, and only recently started LIFD design. So unlike most European countries or in Canada, LIFD has been used by most professionals for a long time. In the United States, it's very recently that people started implementing. Although in the United States, there's a parallel design code. They have ASTO standard specifications and ASTO LIFD specifications, but it was not mandated to use either of these until about 10 years ago. So that's why, because the bridge were designed using different methods, when we talk about load rating, it's naturally different organizations may use different approaches. So what is a load rating? A load rating is just a reverse of bridge design. When we design a bridge, we know that, okay, a bridge has to design for this loading. So we know the loading, and we try to select the member sizes to satisfy that loading requirement. And when we do load rating, it's just a reverse. Load rating is always for the current structures. Like if I see a bridge, I know the girder sizes, I know the deck, I know everything. What I know how much reinforcement inside and so on. So all I need is, I want to know how much load that particular structure can carry. So it's just a reverse of the whole process. So that's what load rating is about. So the purpose of load rating is mainly just to gauge what the structure capacity is, so that I want to know if that can carry my current loading. Or for example, if I see a crack or if I see some deficiencies of the structure, I want to know if that deficiency will make bridge unsafe. So I want to calculate how much load capacity that bridge has. And when we design bridge for that particular loading. And each code usually give you a so-called safety factors. If you use a load factor or LFD, if you use old method, you may use allowable stress. And that will give you basically sufficient resistance. In other words, give you such a small probability of failure, and your structure will not likely to fail. Of course, nobody can design a structure say that I have 100% safety. It's always a probability. When the probability is so small, it will be good enough. And that is a compromise how people decide what load factor should be. If it's too load factor, if the safety factor is too big, you have much smaller probability of failures, but then you waste a lot of material on each or every bridge. That may not be a good choice. You may rather compromise, say, okay, I can have such a small probability of failure so that I don't have to design every member is so big. And so that's when you design, that's only one level. But because the bridge was, especially in the United States, most bridges were designed or built during we call it interstate bomb. When United States, after the Second War, United States developed a national highway system, which is called interstate system. I don't know how many people have been to the United States. Wow, almost everybody. Okay, so you all been to interstate system. Interstate system is a national system which does not allow any traffic lights. In other words, it's always, you can drive always continuously. unless there's traffic jam, which is normal. So therefore rating, because most of these bridges were designed by that, at that time, most bridges were designed for, we call it HS20, which is basically just a 20-ton truck. And since then, the trucking industry dominates the United States commerce. In other words, vast majority, I would say, I don't know exactly, probably 80% or more, the goods shipping around from ports to designated area by trucks. The train percentage is very small, probably 20 to 30%, that range. So this industry keep on adding more capacities by building bigger and bigger truck. That's why the truck industry produce a much heavier truck. Now the design code also have to accommodate. But most of these bridges already been built, and because we know that when we build a bridge, we have bigger safety factors. And if we use the design safety factors to gauge the current bridge, then you will find probably more than half of the bridges unsafe. What do we mean unsafe is that probably the probability is relatively high, but very, very small, still very, very small. And then that will give a perception of unsafe system, which will alarm the public. So that's why the researchers say, okay, we should not use that design standard to measure the current bridge, because the design was designed for that truck, and now we have bigger, heavy truck. So that's why they developed a two-level system, one called the inventory level. Inventory level is very much the new design standard. The factor of safety, load factors are using that. But again, that level may be, the bar is too high. It's like a lot of people may not be able to jump over. And then they say, let's have another level. We call it operating level. Operating level effectively say, okay, if I have a beta, which the probability of failure is like 3.5 was originally designed. If I load to I don't know, maybe 2.5, something like that, and that will be still safe enough. Besides, these bridges are 40, 50 years old, and I don't keep them forever. Probably I only keep them 15, 20 years. And the probability of failure a little bit high is okay. That's why we develop another level, which is called operating level. That level will make most bridges seem safe on paper, but in reality, it's still safe. Bridge has big redundancies, and if any member simply yield, does not really cause any problem. And also because loading is very transient, it just come out and go. Not like buildings, people sit here forever for many, many hours. So that's why it's not a big issue when we have a dual system. Basically, the loading general equation like that. The rating factor is the C is the capacity. The D is the dead load effect. In other words, when we load rate a bridge, people say, well, I know the dead load is already there. I don't care because I cannot manipulate dead load. All I need to know is how much live load that bridge can carry. So basically, I calculated my structure capacity. I subtract my dead load components. And then I use that and divide by my live load effect. So if that is greater than 1, it's safe. If it's less than 1, it's not really unsafe, but its rating is less than 1. So you may need to do some kind of improvement. So that's how rating. This A1, A2 is load factors for dead load and live load. I is impact. Impact is typically we consider part of the live load. So impact is very much when a truck passes over, because it's not static weight. It's dynamic. There's suspensions and Also depending on how smooth your roadway, like bridge surface is. And also it's a big function of the vibration frequency. If we have bridge vibration frequency and the truck suspension frequency matches, they have big impact. If these two frequencies are very, very apart, they don't get into similar frequencies, that usually is not the issue. That's why it's really a function of the characters of the bridge. So that's where the general equation of. So in other words, if you know this equation, and you very much, I don't need to talk about anymore. All you need, you know how to calculate member. Basically, that's seed capacity. In other words, you may have to calculate every major component of the bridge. It's like you calculate all the girders and like a pier band and that kind of. Typically, you only calculate superstructure, substructure, for example, foundation, because we don't really know what foundation capacity. In other words, your calculation accuracy is so vague, it's too inaccurate. Calculating does not produce anything. That's why we usually just look at based on inspection. If you don't see problem for foundation, you don't need to do calculations. So that's if you calculate all the major components, you may get the rating factor for each of these components, and the smaller is the component will be your rating factor for the whole bridge. And a lot of older bridges, I said, using allowable stress design. The really problem of using allowable stress is not probability-based design. So that you may design, just like if you make a chain. Like I saw a lot of people using chains near roadway to block at night to block out to prevent people from parking. You see, each of these chains will have very much similar sizes. But if you make a chain, some like big, some like small, and put together, these big ones really don't help. When you stretch it, the weak ones will break. So that's what allowable stress design is. They build different sizes of chains, and so if you rate for allowable stress design, you will get a lot of different rating factors for different components. But only weak, smaller ones will cover. But if you use LFD design, each of these members, if you design properly, will have very, very much similar factors. In other words, your chain is very much same size. So it gives you much, much more efficiency when you do the design. Yeah, so again, there's different, like 3 types of rating and 2 codes. The allowable stress and load factor was we call the old ASHTO code. We also call the standard specifications. These are the same book. And when you do that, you need to rate many, many different varieties of vehicles. Actually, the example I gave you early this morning, using that, you see different vehicles, different types. For LFD, there's only one truck, which is called HL93, which is like a standard truck. And then you only need to rate for one. So that's why LFD rating is much easier. People may say, why don't everybody using that for rating? The reason is that low rating is something like it's mandated by federal government. You have to do that. And a lot of bridge owners say, okay, I know every bridge is okay because we do low rating every 2 years and there's no much condition change. But if I change the method, and I don't know what happened, I may have 3 bridges which loaded less than desirable, then I have to spend money to fix it, and I know the bridge is okay. So that's why people have tendencies of not one change until these old bridges has been phased out. And so then, but since that method has been, standard LFD method has been used for more than 10 years now, and eventually everybody will be using that. To do relating, either you only need to rate for one truck. Allowable stress, again, allowable stress does not have load factors. So effectively what it does is that, so all the load factor equation will be 1, so there's no load factor. So the difference is in the capacity. Capacity will be the allowable stress. So the allowable stress typically for the design is like 0.55 FY yield stress. That will be your allowable stress for bending, and for shear will be a little bit different. So that's the design. So anything match the design standard is called inventory level. So how do I do the operating level? Because I cannot have different load factors. So for operating, what effectively you do is that you increase the allowable stress capacity. Instead of 0.5 FY, you're using 0.75 FY. So once you increase the allowable stress, you effectively increase that rating factor because all the rest will be the same. So you'll have a higher rating. So in other words, if you use that 0.75, and will not really give you anything in a dangerous situation, although it's not desirable. Load factor is different. Load factor is that the capacity is the same no matter how you calculate, because that's based on the performance factors of each and the different material and different equations can be bending shear. Like for example, for bending, concrete bending, the performance, some places also call resistance. That in the United States, that's what they call resistance factor, like it's 0.9. For steel, it can be 0.5. 95, or sometimes even like a 1, because steel has better certainty of strength than concrete. Concrete, we know we have like 5-cylinder test, that each of these will have different results. So that's why it's a probability basis. So whenever we have different, but that will be calculated no matter what level it is. So then for the inventory level, we use like for F.ASCE design, the live load factor is 2.17. Dead load factor is 1.3. So we use the live load factor, dead load factor times that, and live load factors that's for inventory, which is same design. And we rate for operating level. That does not change. So what changes is that it does not change. It's still 1.3. And we use 1.3 for live load as well. So you'll see, like if you lower these factors, live load factors, effectively you increase the rating factor. So actually, if you look at people's rating calculations or rating data, you will know what measures they use, whether allowable stress or load factor. But if they use load factor, the inventory rating is always proportional to operating, because it's just like a 2.17 divided by 1.3. That will be the ratio between inventory and operating. That's how much you increase. So which is like if you calculate the inventory, you know the operating level will be 1.65 of the inventory. So for the load factor rating, and they also have to use for pre-stressed concrete. Is a pre-stressed concrete bridge popular here? Yes. Okay, yeah. Actually, pre-stress is different. I'm talking about old F.ASCE. Old F.ASCE have allowable stress design and load factor design, but that was before pre-stressing concrete was introduced. So when the pre-stressed concrete was introduced to the United States, mainly by a professor from University of California in Berkeley, his name was T.Y. Lin, and later he formed the company and worked for him for several years before he retired. Then at that time, most countries already use LFD. So when that pre-stress was introduced by F.ASCE, so they just use same concept of LFD, so that there was no allowable stress design or load factor design. It's just a combined one design. If you combine one design, you design bridge for not only the safety, but also for serviceability. Safety means what bending and shear capacity is. For serviceability, you also need to control cracking and deflection, that kind of thing. So that's why when you design pre-stress here, you also have to, for what kind of design code here? You have your own design code for bridges? In Costa Rica, do I have its own bridge design code, or use a Euro code? Oh, you use ASHTO. Now you use LFD. Okay, yeah, that's good. So did you use standard specification before? Like allowable stress? Yeah. Okay. Yeah. Okay. So very much the same. So you have we have common languages here, and that's why you need to also rate for concrete tension and concrete compression. For concrete intention, times square load of FC is allowable tensile stress, and this will be a permanent stress. Permanent stress includes dead load stress and pre-stress and secondary stress. Secondary stress is mainly for post-tension. When you do a post-tension, you may have change the shape of superstructure, but because you have a redundancy of support, in other words, you have different support to restrict you from post-tension. For example, if you have a continuous two-span beams, and you have support and a middle support P and 2, and then you have a cable which represents a shape of bending, and when you pre-stress it, if you imagine the girder has no weight, when you post-tension, the whole girder will try to bump up of that shape, but because of the weight, the weight will balance out, does not actually bump out, so you still have a support in the middle. But the middle support is before post-tension, if there's 20 tons, after post-tension, it becomes 10 tons because of weight. Otherwise, it will go up. So now we have 10 tons, which will almost equivalent force to pull it down, and so that to make it support. In other words, you produce an additional bending moment of these. A lot of people may think it's imaginary bending force, but actually it's a real bending stress, bending moment. That's why in the design, the secondary stress bending forces should be calculated, should be part of the design. It's not imaginary. And actually, if you look at ASHTO, the only load factor which is 1.0 is secondary stress, because that is mathematically determined. There's no distribution of any type. So that's why that is certain for certain bending moments. We have load factor of 1. Every other has distributions. We have different load factors for different things. So that's where that is. So altogether, we call these 3 components as permanent stress. So permanent stress is just like dead load. You cannot do anything about it. So that's why my allowable stress subtracted by these permanent, that's giving me how much stress I can use for the live load. So then that's a live load. And the stress, that will give you rating factors. And the compression is the same. And also post-tension, the pre-stress or pre-stress stress, the steel itself is 0.8 Fy is allowable minus permanent and divided by the live load where you have that. So that's also for stress itself, and so that the concrete won't crash or crack because of overstress. And then there's a capacity. Capacity, these are This is the resistance, the total resistance, which can be bending, can be shear, can be compression, can be anything. And this is factor at dead load. And that's why there's no factor which is 1.0 for a secondary stress. And these are the live load factors. These will give an inventory stress. This is the equation for the design as well. So for operating, as I said, we're mainly concerned about safety. In other words, operating level is where just a load bar so much most people will be able to jump over. And it's the same, so that most bridge will be able to pass. And we don't want have too many things attached to prevent people from passing over. So that's why we have another questions. LR, load resistance factor rating, is like more modern rating methods, and which will be used eventually by all the bridges. So that's very, very similar to load factor methods. Load factor methods and LFD does not have much difference. The major difference is a philosophical difference. One is a probability based, another is not. And that's how the inventory and operating was defined. So for inventory, we use a probability of liability of beta index of 3.5, which have that probability of overstress. Keep in mind, overstress does not mean a collapse or failure of any component, not to mention the whole structure. So in other words, if you have that much chance of one beam may yield or that kind of thing, it's not a really big problem. And operating level, we define the beta of 2.5, which has 1/160 probability of just a simple yield of any members of the structure. So and there's a flow chart, like when you do load rating. So like first you rate HI 93, which is a new design truck, using inventory, basically just the same load factors for the design. And if that rating factor is greater than 1, then that's complete. You don't need to do anything. And if load rating is less than 1, then you just rate for operating. In other words, you lower your live load factors to see for operating okay. If operating rating is greater than 1, then you don't need to do anything. And if the operating is less than 1, then you just rate for legal rating. Again, in the United States, there's no national standard for infrastructure. It's only like a state government regulate. So each state may have different legal law, which typically is lower than the design law. The design law has to be an envelope of national standards, so it's always bigger, large, heavier than the legal law. So each state has a legal law, but ASHTO also have a modern legal law too, if the state does not have its own legal law. So because the load is smaller, you're just using that to rate. If it's greater than 1, then it's okay, don't need to do anything. And if is smaller than 1, then you need to do two things. If you don't do anything, you need to provide a posting. In other words, you say, okay, there's load restrictions and what kind of truck can pass. And otherwise, you need to do a rehabilitation. But because there's a lot of such structures, and people realize that a lot of bridges, when you do the calculation, it does not work. But if you go to bridge side, take a look, and when the truck comes over and has no problem, and then it means the truck is okay, the bridge is okay. So like for these type of bridges, they actually allow you to have another avenue to address that. You can do a load test. Load test is not really just test the bridge to see how much load it can carry before it collapses. Because if you collapse the bridge, there's no way to save it, so it doesn't serve your purpose. What load test does is, actually we'll be discussing that later, is to put a load to see how accurate the model is. Because when we design bridge, like for example, how much live load each girder will be carried, like percentage-wise. And so that is usually not accurate. It's always like a common denominator. It's always like on the safe side each step. So when you do a load test, you may find like actually the distribution of live load is different than you assume. That may work. So if you do load test and reanalyze it, then probably they'll be okay. And another thing that, since F.ASCE is probability-based, so we also consider like old ASHTO does not consider the conditions of the bridge. So now we also have factors to address conditions. Like for example, if we have two identical bridges, one is old, one is new, we know new bridge has better load resistance than old bridges. But if we just simply do a calculation, they're exactly the same. So that's why we have modification factors to new ones. And also how critical the bridge is and how heavy. Like if a bridge is, just exaggerating, have one truck a day, another bridge have 100 trucks a day, although exactly the same, the probability of failure of 100 trucks a day is 100 times more than one, because it has 100 a day that has 1 day. So it has different probabilities. So in order to make the same probability, the heavier the truck traffic has, the more resistance you should have to get equal. Another key element is fracture critical element. In other words, if a bridge has redundancy, then I'm not worried about that bridge too much. If another bridge has no redundancy, I have to take care of that. So all these factors were factored in the new F.ASCE approach. And so these are basically the factors to take a consideration of different scenarios and different conditions. And so this was also a modification for the track like a volume, as I said. Different volume has different. And so for the permit, the same. If you apply for like a permit load, it would really depend on if that permit is for annual. In other words, if I have a heavy load, I have to carry like routinely, like for example, if we have a transformer manufacturers around here, and the transformer is very heavy, and then he will have to design different configurations for bridge, and then once designed, the bridge is okay. But if he only have one transformer pass that bridge only once, then the permit is like single-use permit, then he may have less restrict requirement. In other words, the smaller load factors. And if you have to transfer like every day, it's almost like a routine operation, which means like an annual permit, then that load factor should be higher, almost to like a regular load factors. And also impact, we said the impact is factor of different conditions. So if we have a very, very smooth bridge, and the impact will be very smaller. And if we have very rough surface, the impact will be larger. That only addresses smoothness, but in reality, the impact is also a function of frequencies, as I said. So you can actually slow down the truck so that to actually make a frequency, the impact much lower. or you can do a load test, like if you have very, very long span bridge, like suspension bridge, for example, their frequency is very, very low, and your truck frequency is very, very high because they don't match at all. So you can actually do a load test to see what the impact is, and probably it will be almost 0 or 2% or 3% range instead of 20-15% range, so that effectively you can increase your load capacity to pass over these bridges. So the legal load, as I said, we use there's different type of legal load. Legal load we use only if your actual load cannot pass. In other words, if actual load passes, you don't need to use legal load. And if actual load does not pass, you use legal load to make sure that the bridge is okay. If legal load does not pass again, then you will need to post. The posting is based on these type of legal load. You rate each of these, and then you just say how many tonnage of that has to be restricted. These are the equations. And if the legal load rating is less than 0.3, typically in the United States, you are not even allowed to post. You have to shut down the bridge and do a replacement or rehabilitation. Load rating examples, I have quite a lot of load rating calculations, but I think because of time constraints, I don't think I can give it all. So all these rate calculations are done by actually MassCAD. And that's what actually I've done that almost like 15 years ago. At that time, load rating software is not very popular. But load rating is very, very tedious calculation, but it's not complex calculation. So that's why MassCAD is very good. It just only need to change a couple of characters of bridge, like span length, the girder spacing, girder member sizes, and then you can use it repeatedly. I don't know if MassCAD is popular here. How many people knows MassCAD? So it's not required for doing homework at universities. In the United States, because student version of MassCAD is almost free and very, very cheap, so that typically professors require students to submit homework in MassCAD. So professors don't have to go through calculations, only need to look at the equation to see if the equation is right, then the answer is right. I don't like a spreadsheet, because for spreadsheet, you don't know what's inside, so it's difficult to review. And also MassCAD, once you change this a couple of numbers, you can just print a report repeatedly. That's why it's increased productivity quite a lot when I was doing. But in the first slide, I had my email address. So if you need, just send me an email. I can email you the MassCAD files you can use, or you can use a reference in the future. So that's why today I may not go through all these calculations, but I'll give you one so that you will have very much sense how these calculations were performed. So, this is a very simple bridge. We call it a winch load bridge. Winch load bridge is a steel girder bridge. It's a 3-span bridge, I think, with a slab on girders, and these are typical sections. So again, it's because MassCAD. So if you use MassCAD, you will actually if you never use MassCAD, you will still be able to read. It's just like very much like when I was a student and I started learning computer. At that time, there was a program called Fortran, and the Fortran program is you just write it almost like English, and now programming is a lot simpler. So this MassCAD is similar to Fortran. Once you define, if we say A equals to 20, and every time later, if it says A, it knows 20. But good, even better is that in MASCAD, it has units. If say A equal to 20 centimeter, for example, then later, if we see A, it's not 20 centimeters. It's not 20 meters. So that's where in MASCAD, like, so first you define that's the span arrangement. So, and whenever you see equals, actually these are just the testing description. When you see these two dots and the equals, it's an equation. Like for example, spacing, good spacing is 6.5 feet, which means later, anytime if you see a spacing, it represents 6.5 feet. So later, all you need is just give equations, and you don't have to do anything like that. Like that's yield stress, and that's the deck thickness, and that's hunch. Hunch is the little bit of concrete on top of girders, and that's the strength of concrete strength. So the case that was very low for a very weak concrete was old bridge. And then you calculate there's a unit weight of a concrete, which is 150 pounds per square feet. And that's a unit weight of steel, which is 490 pounds per square feet. I assume here people use metric, right? Yeah, I use metric for most of my life. So only when I moved to the United States, I started using English units. And actually, at that time, a lot of states use metrics. And later, they, like for example, like Texas or New Mexico, they use metrics, and later they converted into English, and now everybody uses English units. And so like this deck is a calculate weight, like how much weight per strip of girders, and that's deck thickness times spacing times the unit weight, and so on. You calculate all the weight, and then and like hunches and so on. Later, that total, you add it all together, the total like unit weight, in other weight, how many pounds per square foot per girder, that will be a concrete dead load. And then you calculate the, okay, sorry, did I? Okay, so then you calculate dead load bending moment. I did not want MASCAD. I did not want to program a monster language to just simply calculate continuous beam bending moment. It's either I just use another software to calculate bending moment and use that as input. So this will be input. That will be a lot simpler. If it were simply supported, I could just program it as 1/8 and such got a bending moment. So that I use another together. So that will be also shear, like a reaction, shear forces at these, and then that's a dead load. And then I do the same for the superimposed dead load. And superimposed dead load is like a dead load after the girder is erected. After the deck is hardened. So once deck is hardened, the deck and the girder become composite. So once you apply, like for example, a pavement on top or railings, or you add like utilities, these will be added as dead load, but we call superimposed dead load because that has resisted by a composite girder and the deck sections. So we did the same for these. And live load, that bridge was rated for HS20. HS20 is exact same live load configuration as HL93. HL93 is HS20 plus a uniform distributed load combined. So it's very heavier than HS20. So then the live load again, and I I did not want to program it, so that I use another software to calculate live load and then as an input into these. But basically, I know, because it's a 3-span, I know the critical elements for bending is the midspan. Midspan is longer, midspan positive bending, and negative bending over the piers. These are the most critical. So I only calculate these. And so for sections, first you have to calculate like a non-composite sections. For non-composite sections, because that's actually the standard W section, we call wide range section. You can look at manufacturer's category. You will get like these IAS just from these standard. If it were a customer build, like a steel plate girders, then you actually you can calculate these from these sections. And then you just calculate calculate bending moment. They did, because these were using allowable stress, so you have long-term effect and short-term effect. For live load short-term effect, because live to come and go. And superimposed dead load is a long-term effect, although they both are for composite section. So that's why one has different ratios of E. So this is just very much I convert my concrete, because deck is made of concrete, girder is steel. Because I have that white concrete deck, but then I just convert it into steel, so I just shrink that width by the ratio of the E modulus of steel and concrete. In this case, it's about 10. Actually, it's about 9 something. I just simplify using 10, so that then I get composite section for that. And then I just calculate the superimposed dead load. Superimposed dead load, again, because superimposed dead load is permanent, so that effect is larger than live load come and go, so that the ratio is even smaller. In other words, my concrete deck was that wide, I shrink by 10 like that. That's for live load. But for permanent superimposed dead load, I even shrink further, become that much to calculate my composite sections. And so that for the positive bending moment. For negative bending moment is relatively simple, because the concrete over here, the concrete will be in tension. So when concrete is in tension, we typically ignore it. And so all you have is a steel girder and also the reinforcement in the deck. So it will be just a reinforcement and the steel girder as a composite sections. So that we know what reinforcement is, and because they have top layer, bottom layer, so you've got the average where the reinforcement is and what the member size is. So you've got effectively a big rebar here and a steel girder here, and that will be a section. So once I calculate the section properties of S, and then I will be able to calculate the dead load stress, which is like a normal dead load divided by net section, and superimposed dead load divided by composite section for superimposed dead load, which is like a 3n ratio. And the live load is my total live load. Live load always includes the impact. And then divided by my live load section properties. So I have that much stress for total dead load and the superimposed dead load. And I have that much stress for live load. And the concrete at top, I also calculate concrete at top, so just make sure that the concrete won't crash. So the concrete, the stress for compression and for dead load, and for dead load, actually, the girder itself does not produce any concrete deck. And also the concrete deck, when you pour a concrete deck, the concrete is very, very soft. So the deck itself does not produce any stress. In other words, the only dead load stress is superimposed. Later you do the pavement, you install railings that will produce a little bit of stress in the concrete. And so the main is the live load stress. So then the rating is like, once you calculate the total allowable stress is like for inventory 0.55 for bending. Then I calculate, subtract that by total dead load stress, which is calculated in the last page, and divided by total live load stress divided by last page, I got 1.35. And then I calculate concrete in compression and rating factor, that total factors for that. That's for the positive bending. And that's the operating level. Operating level, as I said, we lower the bar lower so that instead of 0.55 Fy, the allowable stress will be 0.75 Fy. So that these are like dead load stress, live load stress is the same as before, but this allowable stress is bigger. So naturally, because this is bigger, that's the same, so you got a bigger rating factors. And the same is true for the allowable compression in the concrete. So the positive bending inventory stress is that operating stress is that operating is always larger than inventory. And for then that's your positive bending, because these are like you can select a positive bending, because positive bending you have two scenarios. One is in concrete, one is in steel. So it's found in the steel it's more critical than in concrete. In concrete, the rating factor is bigger, so you always select the smaller. Then the negative bending. Negative bending is the same. Like you calculate the negative bending moment for dead loads, and they calculate negative bending for live loads already calculated. You just divide by their section properties. So we got a stress for the top flange of compression, and tension, and this top flange actually calculate bottom flange of compression and this bottom flange of live load compression. And then you also calculate reinforcement, because in a negative bending, reinforcement in the deck is in compression. And then you just calculate the dead load. Dead load only for superimposed dead load. The self-dead load has no stress. And they calculate live load divided by that composite section. Then you just calculate the inventory, like inventory allowable stress is like that. Then subtract by total permanent load stress by live load stress, and if that's the rating factors for a point for negative bending, and you do the same for the reinforcement. So in that case, the steel girder controls. And you do the same thing for operating level. Operating instead of 0.55 Fy, you use 0.75 Fy. Once you increase these numbers and the rest is the same, so effectively have bigger rating. So effectively, you just select the least. So the bending for the girder controls, negative bending for girder. So that's the inventory is 0.93 and operating 1.9. So it because the posting requirement or rehabilitation requirement is from inventory, so it still has like 90% overcapacity, so you don't need to do a rehabilitation. That's why from this you will see why there are two levels. Once you have second level called operating level, vast majority of bridges will not need to be rehabbed. Otherwise, it will be a disaster situation for finance. the shear is the same. So the shear capacity is shear stress is like first you need to calculate the girder shear area. Girder shear area basically just take out the top and bottom flanges, just a web only. That's the area, and so you have total dead load stress. You have dead load shear, superimposed dead load shear divided by area. You got that's dead load stresses. And live load stress is you have total live load shear divided by that area. You got live load shears. So for the inventory level, inventory is the same as design. The allowable stress is 0.3 Fy. So you have allowable stress, which is that subtract the dead load and divided by live load. So you get a rating factors for the shear. That's the inventory. For operating, the same. Operating, instead of using 3.33, use 0.45 as the allowable stress. Once you increase the allowable stress, you effectively get a bigger rating factors. So after you get negative and for final rating is, if you calculate all the different components, like the girders, positive bending, girders, negative bending, and others, we don't usually rate for deck. The reason we don't rate for deck, we find deck is always way over designed. So that's why a deck is not need to be rated. And again, substructure don't need to be rated because substructure has such a big uncertainties. Calculation does not mean much. So then you have a negative bending, positive bending. Then you just select the worst rating. So in other words, in this case, negative bending have a control. So the total bridge rating will be 0.93 for inventory and 1.9 for operating. Again, the rating factor is always linked to the rating vehicle. Without saying what rating vehicle, it's meaningless to say what rating factor is. Like for example, if you rate for HS15, for example, your rating factor will be that times 20 divided by 15, so your rating factor will be much larger. That's for old edge though, in other words, using allowable stress design typically. But if you're using LFD design or rating, then the vehicle is only one vehicle, HL vehicle. So we have other examples, and like for example, we use load factor design and allowable stress design. But again, we don't have a lot of time for that. So feel free to send me email. I can forward you the rating calculation, so you can either study or use in the future as reference. Now, any questions regarding load rating? The purpose of load rating, again, is for determining if the bridge is safe enough, and also for selecting as candidates for rehabilitations. Like for example, if we have a rate like for puentes or for any manual selections, you want to select the one with a poor rating. That's for globally. Like individually, if you see a bridge, like for example, in this case, and if you want to select it, probably you want to strengthen the negative bending areas. Like if you are replacing the deck, probably you can put more reinforcement in the deck over the piers to increase capacity. Okay, any questions on load rating? Okay, no questions? Yeah, we're approaching to, yeah, sure. Okay.
Yes, I would like to know, when I read, can you back in the slide, please, if it's possible? I read about the rating factor that you have to use in the list of the element that you have for all the bridge.
Yeah, yeah. No, actually, that's an advantage of doing calculation manually. If you do calculation by computer will rate every element and every location and every force. In other words, each element calculate bending shear and so on. So that then when computer has the advantage of fast calculations, they can calculate everywhere, then select the worst situation. But for manually calculation, you have to make judgment. But just by look at what may be the most critical element and what location may be most critical. Like for example, for post-tension, if you have a post-tension cable like that shape, you may select the middle span. Sometimes middle span may not be critical. You may select something like a 0.7, 0.8, that area, because you have your D is much smaller. And so that's why they may calculate, even for the same member, they may calculate different sections, just make sure everywhere is fine. Okay. So in other words, in theory, you need to calculate everything and every element. Like for example, even these, you may need to calculate interior girder and exterior girders because they may have different live loads. But yeah, and also that section probably may, because sometimes the exterior girder may have very small overhead. So that section, like a concrete section, is much smaller than others. So that's why in theory you need to calculate both interior girders, exterior girders. Of course, live loads are different, dead loads are different. Yes.
So in this case, you say that I understand I have to calculate all the elements.
Yeah,
but the thing is that if I have to make a composite of everything, I make a final report. So if I do that, when I do for example, at least all the elements, I will know what element has problem or not. But according to the phrase that I read there, you said that you have to, I know that but you have to evaluate the bridge with the last rating factor that you have. So for all the bridge, so that's my question for you, because I understand that you have to calculate everything by elements, but if you determine the rating factor for all the bridge, you have to use the less one, the small?
Yeah. Once you get the final result, the weakest, as I say, if you bring a link, a chain, and the weakest one will be your capacity. So that will be the one. So that's why I only calculate basically three elements, three critical ones. Shear at the pier, I know that's very critical, and the positive bending in the middle span and negative bending at pier. I only calculate three, so I found the negative bending over the pier controls, which that's why that will be the final report say that. But once you do it, because all these data will be imported if you're using, that's why if F.ASCE develop a software, now a lot of organizations in the United States don't want you to do manual calculation, because not only they want to know the final rating, they want to know the rating for each element, so that when punters make decisions or make recommendations, they look at these, they may say you need to fix this, fix that, because of these rating calculations. So, and also if you do a manual decision, just look at say, okay, like for example, if we have a end span bending, calculated end span bending is because the section is smaller, I just assume this is actually constant. If we have smaller section end span, although it's shorter, and it has actually significant bending, and then you find that is insufficient, then you probably need to fix that over like a negative bending, and that, although that may give you 0.95 for them, and it does not even show, because 0.93 will show in the final document. Although if they look at your calculation, of course, it will show up. Okay, what's your next question? Yeah.
About what's the tolerance about, for example, the error on this method that you, in your experience, the error that you, for example, when are you making the calculus, you suppose that the structure has a problem, but and you show by your calculus on your final report. But I would like to know your error that you have been discovered by yourself. I would like to know what it's been about. If you check that is happening, how are you calculating it?
If you want to check other people's calculations?
Yes.
Yeah. It depends on how people do calculation. Nowadays, most people use software which is called Astro Bridge, because that software output is linked into puentes. But again, if you use like manual calculations, then before I use like, if I don't like it to check people's calculation. I like rather to calculate myself just to see if I get a similar answer. So that's how you calculate. Actually, I think because the low rating was not taught at any university like a long time ago. When I studied, I think in 2005 or 2004, that time, there was a research by the Federal Highway Administration. They randomly sampled about 20 low rating calculations. They found that almost like 50% of these calculations had significant errors. And that's why the Astro developed a software. So the software has good part or bad part. Good part is that if you have good input, it should be very accurate. The bad part is that if you don't have good input, or if people don't know. That's why for anything, like if you want to use software, you should be able to ask yourself, can I do that manually? If you cannot do it manually, it's always questionable because you don't know what comes out of the software. Even if I use software, I always do some very, very quick manual calculations to see if it's in like a accuracy range in that magnitude. Again, just like anything else, manual calculation is become like less and less. But again, for any structural design, probably it's always required to do a very quick hand calculation just to see like what output, whether the output makes sense. Yeah, second question.
Yes, my second question is about what kind of software do you use to make the calculation?
Usually software is like, most bridges are owned by public organizations, and each organization has a requirement of what you must use. Like at the beginning, most people do hand calculations and develop their own spreadsheets, or mascot, that kind of thing. And later, more and more state has requirement of using certain software. So you have to follow that. And hand calculations are not very common unless like you work for a small organization like a county, for example, or a township, where like they have only 20 bridges and they don't have any like management systems. All they need is a hard copy report they can put into a drawer. And in that case, you can use any software or no software at all.
Just a comment. We use a CSI bridge.
Yeah.
Yeah, they have load rating factor.
Yeah.
Load rating
Right.
model to use this.
Mm-hmm.
But some of the case, I don't trust on this. So I think because you have to calibrate your model, I think the model, the bridge that you are analyzing.
Yeah.
So that is very difficult to just for
No, actually, we have a lot of similar situations. My recommendation that you just spend like $20 or free. You can download $20 from Pennsylvania DOT. They have like very, very old software, like fortune-based software, and do low rating. Or you can go to Florida. They have free software do low rating. You can use that as a check just to see if once you have a developed program, to see if, especially once you buy new ones, to see if they work. In many cases, it does not work because the user misunderstands the input. The input wrong. So it's always very useful to just to calculate to see if I get similar output. If I get similar output, I know I use that correctly. Or if it's a new product, you may say, well, that product may not be accurate. Yeah. But for like popular products, I think typically it's being calibrated by many, many different users and it should not have big problem. Most of the problem you may face is the assumption whether it's curved and you assume it's not curved, or it's heavily skewed, or something like that nature.
Thank you.
Any more questions? Yeah. Okay, if not, then we can have a...
Maybe I have a question.
Sure, yeah.
What could be, in your experience, a practical consequence of having a bridge that meets the requirements of the operational load, but it has a value less than 1 for the inventory load? Is there a practical consequence in terms of something that has to be made?
You mean if they don't meet the rating requirements?
No, if it meets the requirement of operational load, but it doesn't meet the requirement of inventory load.
Yeah, and these are typically for older bridges. If it's for new bridge and you have such a situation, which means the designer made error, or you made error in calculation, either way, somebody must have made error. But for older ones, the reason was, there are two reasons. One is, when they designed, it was designed for a lighter truck, so you may end up such a situation. And the whole purpose of having dual system is to prevent public panic for the funding, which for funding level the governments currently have. In other words, you want to have a smaller funding as possible, which politicians don't usually like to have a lot of money. They say wasted, but it's not really. And on the other hand, they don't want public has big panic, say, okay, our system is not safe anymore. So that's what the whole purpose is, that for that purpose. In other words, it translates, governments don't want to spend that much money to bring that level to even operating level. So in other words, they will think inventory level is good enough. So that's why for all the rehabilitation, especially for posting purposes, operating level is used. But inventory level, again, is used for design. So if you have a new bridge, you have such a situation, probably you need to find out why. Especially if you use different methods, like most bridges were designed use allowable stress. And the allowable stress is designed that it's pretty safe. It's like an overall, because allowable stress, you spend a lot more materials than otherwise. In other words, so the overall safety for like each component is larger than the LFD method. But because it has big and evenness, so some elements might have smaller safety factors, but I haven't found that. Like I read a lot of bridges was designed for allowable stress, and they always have big rating factor for LFD method. But nobody knows. It can be a certain chain which was built very small, and it may just show up somehow. So again, because the difference of inventory and operating is so big, it will be extremely difficult to catch any fish, like a net of that big hole. you try to catch fish, usually don't catch any. Occasionally catch a couple of big fish, so you need to repair. Otherwise, it's just all fish passes and you have no problem and everybody's happy. Okay, any more questions?